In this lecture we will go through one of the very important reactions of alkyl halide, right? Elimination reactions. We are already introduced to elimination reactions in our previous chapter, mechanism of organic reactions, right? So here we will see how these elimination reactions occur in different types of alkyl halides, right? And we'll understand two important rules that are related to these reactions, elimination reactions: Saytzeff's reaction and your Hoffman's rule reaction. Hoffman's rule, right? So Saytzeff's rule and Hoffman's rule would be important, right? Which we will understand through these elimination reactions and are applied to these reactions in order to find what product will be formed, right, by elimination reactions in alkyl halide, right? The products formed would be decided by Hoffman's rule and your Saytzeff's rule. So alkyl halides, when treated with alcoholic caustic potash, they will undergo elimination reaction. Elimination simply means atoms would be eliminated from the same or adjacent carbon atoms, like we have done in the previous lectures on elimination reactions. So here the elimination reaction that we will study in this lecture would be beta elimination, if you remember, right, where hydrogen atom would be eliminated from the beta position, right? And beta position is the position next to the carbon atom to which your halogen atom is joined in haloalkanes, right? So let's take example of simple alkyl halide, right, which is your ethyl bromide, right, this. And one more thing, beta elimination reaction will always result into the formation of alkenes, right? So I'll just write it over here. Beta elimination, right, will always form alkenes. So when ethyl bromide or bromoethane is treated with alcoholic KOH, it will undergo elimination. When we say elimination, to be very specific here, it will undergo beta elimination, where a halogen atom and a hydrogen atom, right, would be eliminated, and the hydrogen atom that would be eliminated would be from the beta position, right? The important thing to understand here is the alpha beta positions, right? The carbon atom to which this halogen atom is directly attached is your alpha carbon atom. Next to alpha carbon atom you have beta carbon atom, right? And hydrogens attached to your beta carbon atom are your beta hydrogens, right? If you have one more carbon atom attached here, that would be gamma carbon atom, right? So here, in the presence of alcoholic caustic potash, your hydrogen and halogen atom would be eliminated, resulting into the formation of an alkene, because beta elimination will also always result in the formation of an alkene, right? Since this is eliminated, now you have a double bond, right? So in elimination reaction, you can see saturated compounds are converted into unsaturated compounds, right? That is, alkanes would be converted into alkenes, right? This is an alkene, which is an unsaturated compound, and this is your alkyl halide, which is a derivative of an alkane, right? So this compound is formed, and since if you look at this reaction, hydrogen and halogen is removed, right, from adjacent carbon atom, the hydrogen and a halogen atom is removed. We call these reactions as dehydro. D means removed, hydro stands for hydrogen, dehydrohalogenation. Dehydrohalogenation reactions, right? D means removal, hydrogen and halogen, removal of hydrogen and halogen. These are dehydrohalogenation reactions, right? So this is a dehydrohalogenation reaction, a beta elimination. Right, now let's take some other halide to understand it a little more better. Right? If I take this compound, CH3, right, CH3, CH2, then you have halogen atom, right, to this carbon atom and hydrogen atom. In the presence of alcoholic KOH, dehydrohalogenation will occur. That means hydrogen and halogen atom would be removed, right? It will form an alkene, right? Since this is removed, so you get a double bond here, right? So here the reactant is 1 chloropropane, right? And this is your 1 is at 1 carbon atom you have chlorine, 1 chloropropane, and this is your 1, this is prop 1-ene, right, which is an unsaturated compound, an alkene, right? So here you will write it as prop 1-ene. 1 represents position of double bond at first carbon atom, right? So these are two important reactions, beta elimination reactions, right? You can see this is your alpha carbon atom, this is your beta carbon atom. So hydrogen atom, beta hydrogen is eliminated from the beta carbon atom, right? Now if the structure of alkyl halide is such that here you can see you just have one alpha hydrogen, right, one type of alpha hydrogen, but if the structure of alkene is such alkyl halide is such that you have two beta positions, right, you have two beta hydrogens at two sides, then what would be the product, right? That would be decided by your Saytzeff's rule, right? So let me just draw one structure. Right, let's draw it like this. Right, this is your 1, 2, 3. This is your 2 chloro 1, 2, 3, 4 butane. This is an alkyl halide 2 chloro butane. Now if you treat it with alcoholic KOH, since I said this would be a beta elimination reaction, right? Beta elimination means this is your alpha carbon atom, right? This is your, now next to alpha carbon atom is your beta carbon atom. This is your beta carbon atom. Now you have one more carbon atom which is next to alpha carbon atom here. This is also your beta carbon atom. This is your beta carbon atom. This is your beta carbon atom, right? So as per beta elimination, beta hydrogen would be eliminated. That is, hydrogen atom connected to the beta carbon atom is your beta hydrogen atom. So this is your beta hydrogen atom, this is your beta hydrogen atom, right? So this hydrogen atom can also be eliminated along with this Cl. This hydrogen atom can also be eliminated along with this Cl, right? But which would be the stable product out of the two alkenes? So two alkenes would be formed here. One alkene would be formed by elimination of this beta hydrogen atom. One alkene would be formed by elimination of this beta hydrogen atom. But which one will predominate, which one is more stable would be decided by your Saytzeff's rule, right, in case of halides. So let's see the two products that will get formed. right? Which one will be the major product would be decided by the Saytzeff's rule, right? Let's say first this one will get eliminated. It will form CH3 CH C CH3. This is the product. Name is but 2E, right? Now let's say this one is eliminated, right? This is the alkene that we obtained by elimination of this beta hydrogen atom, this one, right? Now let's say this beta hydrogen atom will also be eliminated, because as per beta elimination, beta hydrogens would be eliminated. Now if this hydrogen would be eliminated, this beta hydrogen would be eliminated, then product formed would be CH3, right, CH2, then you have C, right? This halogen would be removed, this hydrogen would be removed, a double bond would be introduced, right? This is but1ene. This is how you will name it. This is but1ene, right? So this is a different alkene, this is a different alkene, right? You can see you have two methyl groups here, you just have one methyl group here. The position of double bond is different, right? So these are some differences between these two, right? So which one will predominate, or which product will formed, or which is the major product, would be decided by Saytzeff's rule, right? And this Saytzeff's rule says that out of these two alkenes, right, the one which is more substituted would be the major product, right? The one which is more substituted would be the major product. This is what the Saytzeff's rule says. So what do you mean by first substituted alkene? If this is an alkene, you have just hydrogen atoms in this alkene. This is a terminal alkene, right? This is a terminal alkene which is not substituted as of now. Right now, if I remove hydrogen atoms and replace hydrogen atoms with alkyl groups, I am substituting it, right? If I substituted more, like this, or if I substitute all hydrogen atoms with methyl groups, this is the most substituted. There is no substitution in this is ethene. Here I have substituted one hydrogen with methyl. Here I have substituted two hydrogen atoms with methyl. In this I have substituted all hydrogen atoms with methyl group, right? So the last one is the most substituted, right? This is the most substituted. So as per Saytzeff's rule, the alkene which is most substituted would be the major product, or would be formed, right, as the major product. So here you can see in this alkene you have one alkyl group, which is this CH3CH2. It is an ethyl group, right? Here this is CH2, this is not an alkyl group, this is methylene, right? So here you have one alkyl group, here you have CH3CH3, you have two alkyl groups, right? So this one is more substituted compared to this, right? So as per Saytzeff's rule, the alkene which is more substituted, right, would be the major product, right? So this would be the major product as per Saytzeff's rule, would form 80%. This would be the minor product, formed as 20%, right? Why? Because this is more substituted right? We have understood what do we mean exactly by substituted. This is less substituted, right? So more substituted alkene would be formed in major quantity, right, as compared to less substituted one, right? This is your Saytzeff's rule, right? So this is important. The one which carries and which is more what do you mean by more substituted? The one that carries more number of alkyl groups, right? Now we'll just look into ease of dehydrohalogenation. This is a dehydrohalogenation. We'll see what type of alkenes, what type of alkyl halides would undergo dehydrohalogenation most easily, right? So this is your more substituted, this is your less substituted. This is important to understand, right? More substituted means more number of alkyl groups, right? Less substituted means less number of alkyl groups. Now ease of dehydrohalogenation. As per ease of dehydrohalogenation, which alkyl halide will undergo dehydrohalogenation more easily, right? The one that will form an alkene, because we know that in dehydrohalogenation alkenes are formed, right? So that halide or that alkyl halide that will form more stable alkene, right, would be most easily, will undergo dehydrohalogenation most easily, right? Here let's see now what type of alkenes, let's see what type of alkyl halides will form alkenes. We'll just understand what type of alkenes will undergo dehydrohalogenation more easily, right? So we'll just take some examples. If I take CH3 CH2 Br, right, this will undergo, one hydrogen would be removed from here, this Br would be eliminated, right? So this type of compound, this is your bromoethane, right? In the presence of alcoholic KOH, it will form right. This is your CH3, it's same, CH3 CH Br, right? In the presence of KOH, it will form this product, right? This is the same thing, right? One hydrogen would be eliminated from here, right, and one would be eliminated from here. Here I've just missed one hydrogen atom, right? Here I just missed one hydrogen atom, right? So one hydrogen atom would be removed from here, one would be from there, right? So it will form this compound, right? This alkene, remember, as per Saytzeff's rule, ease of dehydrohalogenation would also be decided by your Saytzeff's rule, right? So here this alkene is formed, this is not substituted, you have no hydrogen atom, so this is not substituted, right? Now if I take a different alkene, right, let's take 2-bromopropane. Let's take 2-bromopropane, CH3 CHBr CH3, right? So in this case, more substituted of alkene would be formed, this Br would be eliminated and one hydrogen from this beta carbon atom would be eliminated, right? So here you have one methyl group, right? Here you have no methyl group, so this is mono substituted, right? This is your mono-substituted alkene. Right, now let's take a tertiary butyl halide. This is your alcoholic KOH. Right, in this case the alkyl halide that will get formed is this one, right? One Br would be eliminated, one hydrogen would be eliminated from any of the beta hydrogens, right? So this is your disubstituted alkene, right? So this is your primary or 1 degree halide, this is your secondary or 2 degree halide, this is your tertiary or 3 degree halide. And tertiary halides, right, are forming alkenes that are more substituted, right? So as per Saytzeff's rule, alkenes that are more substituted, right, would be formed in major quantity. Why? Because substituted alkenes are more stable compared to compared to alkenes that are not substituted or less substituted, right? So here your tertiary halides or 3 degree halides are forming more substituted alkenes, right? So this alkene would be formed in major quantity, or we say this alkene is most stable as per Saytzeff's rule, right? And this would be less stable because of no substitution, right? This is not substituted. So this alkene will undergo dehydrohalogenation most easily, right? Because it forms more stable alkene, right? Because it is more substituted as per Saytzeff's rule, right? Then comes this 2 degree alkyl halide, which forms less mono-substituted alkenes, which is less substituted compared to this alkene. Then comes your 1 degree alkyl halides, which forms an alkene which is not substituted at all. So this is least stable and would be the minor product, right? So your 3 degree or tertiary halides, right, ease of dehydrohalogenation would be maximum in tertiary halides, which is your 3 degree, right? Then comes your secondary halides, which is 2 degree. Then comes your primary halides, which is your 1 degree, right? So this is the ease with which these will undergo dehydrohalogenation, right? Tertiary halides will undergo dehydrohalogenation most easily. Why? Because they form most substituted halides, right? So this is done, right? Dehydrohalogenation reactions, right? Simple halide. Now if the structure of alkyl halides or the position of this halogen atom is such that it has 2 beta hydrogens, right? So which one would be the major product? The one which is more substituted as per Saytzeff's rule, right? And which alkyl halides will undergo dehydrohalogenation most easily? The one that forms alkenes that are more substituted as per Saytzeff's rule, right? So these are tertiary halides, right? And primary halides or 1 degree halides form alkenes that are not substituted, right? They are terminal. This is a terminal alkyne which is not substituted at all. So this would be your minor product or least stable. So this will undergo dehydrohalogenation with most difficulty, and this will undergo tertiary halides will undergo dehydrohalogenation most easily, right? Now comes your Hoffman's elimination rule, right? As per Hoffman's elimination applies to fluorides. It applies to fluorides, and as per Hoffman's rule, right, Hoffman's rule also decides which alkene would be formed in major quantity, right, or which alkene would be most stable. As per Hoffman's rule, which applies to fluorides, that alkene would be formed, that alkene would be more stable or would be formed in major quantity, which is formed as a result of elimination of more acidic hydrogen atom. Right, remember, alkene which is formed as a result of elimination of more acidic hydrogen. Right, is most stable, is the major product or most stable. Right, let's take an example to understand Hofmann's rule. So just remember, if there is a fluoride, then you will apply Hofmann's rule. Right, and this is based on inductive effect. Right, you can see there is a fluoride, right, that I've mentioned. Let me just write it down here. This is a fluoride. This is your alkyl group. Now we have to see which hydrogen is more acidic. Right, which hydrogen is more acidic. Just remember the plus I effect. The plus I effect of methyl group. Plus I effect of methyl group. You have methyl group here. As per plus I effect, it will release electron, right? Or it's an electron, it has electron donating nature. It will release electron, right, to this carbon atom, right? So you have more electron density on this carbon atom, right? And this we know is a proton hydrogen atom. So in this you have more electron density on this hydrogen atom, due to which it will hold this hydrogen atom more tightly, right? So, and since this is electron donating, right, so you have this hydrogen atom also, right, and you have this hydrogen atom also. As you move away from this methyl group, right, you are moving away from this methyl group, the acidity of hydrogens will keep increasing. This is least acidic, right, and this is far away, right, because this is electron releasing, so this is releasing electron on carbon atoms, right? So this inductive effect is decreasing as you move away from the electron releasing groups, right? So here inductive effect of methyl group would be minimum, right? So this has less electron density, this carbon atom has less electron density. So from this carbon atom, this hydrogen atom can be removed most easily, right? When we say acidic, that means whenever we talk about acidic nature of any compound, that means we are talking about how easily it can donate a proton, right, or hydrogen atom. So this, from this position, this hydrogen atom can be most easily lost.